Okay, so as you can see, the subtopic of our first session is thermodynamic variables. So what are the thermodynamic variables we are going to deal with? Primarily, there are three thermodynamic variables are there. One is pressure, this is volume, and there is temperature. Now these are primarily the three principal thermodynamic variables. Based on this, we have certain other thermodynamic variables, which we say that chemical potential, then there is specific gravity, or we can say there's entropy given by S, enthalpy denoted by H, internal energy G, this is U, Gibbs free energy divided by G. So entropy, enthalpy, internal energy G, and we can also see that there's a work, external work done, and there is Q, heat added or subtracted from the system. So these constitute these are the variables that which are of great concern in thermodynamics. So let's now so these are primarily the important thermodynamic variables which you are going to come across the equations and while solving the problems. Now we'll move to the next subchapter, that is the extensive and intensive properties. So I'll just wipe it down. So write extensive and intensive. Okay. So what are the extensive properties? Extensive properties are those properties which are dependent on the mass and size of the system. So for example, if you are talking about the entropy or enthalpy or energy, anything. So let's say you are talking about the pressure of the system. You are talking about the volume of the system. Okay? You are talking about enthalpy of the system. You are talking about entropy of the system. Anything. If is function of n, that is number of moles or mass of the system, then these are extensive properties. N stands for number of moles, M for mass. What are the intensive properties? Intensive properties are those which are not dependent on the mass or size of the system. For example, if you talk about temperature, this is an intensive property. You can talk about chemical potential, which is an intensive property. For example, density is an intensive property. Cp, if it is not molar Cp, then This is intensive CV, that is heat capacity at constant pressure and heat capacity at constant volume. So depending on whether it's divided by mass, then it becomes an intensive properties. But if mass terms or number of moles terms are included, then it automatically becomes extensive property, right? So this is briefly about extensive and intensive properties in thermodynamics. So remember, anything dependent on mass or number of moles are extensive properties, and which are not dependent on mass or number of moles are intensive properties, like temperature. Yeah. Now we come to the state function. The concept of state function and path dependent functions are very, very important in thermodynamics. So how do we define a state function? Let's say you all know PV diagrams, right? So in the PV diagram, suppose say this is a state 1 and this is a state 2, right? So if I want to reach state 2 from state 1, there are numerous ways I can. So if I want to reach from state 1 to state 2, there are a number of ways to do that. I can find a path like here, find a path like here, and find a path like here. Note, in each of these steps, the energy done by the system are different. So in thermodynamics, the work done by the system is given by P del V, which is written as W. So work done is pressure multiplied by volume. So in certain cases, we have to substitute the pressure in terms of volumes to get it integrated, right? So those are the options. Now we'll come to the state functions that we are discussing. So the final state, say U or U2, the states doesn't depend on the path taken by the process. It only depends on the state variables. That is, what is the final pressure and volume, or what is the final pressure and temperature, or what are the final pressure, volume, temperature. So U, which we called an internal energy, is a state function because it depends only on the final state of the process, not the path taken by the process to reach that state. Okay, so now moving on to the next thing. So but if you see the work done, so work done is a path dependent process. And internal energy is a state function or a path independent process, right? So the U, internal energy, is a path independent process which is only a function of temperature, because if you are fixing P and V, so T is automatically fixed. So PV equal to RT, so it's only a function of temperature. But the work done, which is actually the area under the curve, so in these cases, the work done are different. So it depends on how the process moved to the final state. Fine.